I'm fortunate because these are all students in my class, CS249, Data Analytics and Visualization this semester. And their task, although it started about 2 weeks ago, it was to work with historical data from the Ruhlman Conference programs, and they will tell you about what they've learned during these 2 weeks of ongoing process of data science with Ruhlman data.
Okay, great. So welcome. So as many of you may know, this is the 20th anniversary of the Ruhlman Conference, and a little while ago, the Ruhlman board approached our class and asked us if we could look at the past years of the conferences from a data science perspective, and our class is a data science class. So what we took from that was that we were going to look at data from the past year's programs and answer questions like, what major dominated the conference, or what advisor advised most students, among other things. So this is us. My name's Anne. I'm a computer science student in the class of 2018.
I'm Clara. I'm a computer science and biology student in the class of 2018 also.
I'm Jackie. I'm a class of 2018 computer science major.
I'm Meredith. I'm a class of 2016 math major.
I'm Christina. I'm a class of 16 political science major, computer science minor.
I'm Hannah. I'm 2019 Undeclared major.
My name is Kate. I'm a class of 2018 computer science and math major.
I'm Nina Marie. I'm a 2018 computer science and sociology major.
I'm Whitney. I'm class of 2017. I'm an MAS and Chinese minor.
You can call me MR. I'm a 2017 computer science and Italian double major.
My name is Maya. I'm a sophomore computer science student.
Again, our class is CS249, Data Analytics and Visualization. So the intention of this course was to introduce students to collecting data, cleaning data, analyzing data, and visualizing data. And our class is a very diverse group of students. We come from all sorts of majors, including the typical like math and CS backgrounds, but also biology, economics, and political science, among others, as well as all levels of experience with both computer programming and data science. So today we're going to talk to you first about what data science is in general. Then we're going to go into how we got the data we got for the Ruhlman programs, and then what it took to analyze and clean that data, as well as the discoveries that we made with that data and what we could have done better and improved.
Okay, so it's actually really interesting to see what all the abstracts kind of towards in the Ruhlman Conference. So over the last 20 years, we accumulated all the abstracts, and the top 23 words that were presented in at least 10% of all abstracts are the ones depicted above in this word cloud. And it's really interesting to see that it's clearly a conference about women, about research, about studying, about Wellesley. Yeah. So apart from that, we also did abstracts for different years and created word clouds. And it's really interesting to see how every year kind of has a different focus. It's interesting to see, for example, in 2003, there's a lot about America and about state, social, school. Maybe this has something to do with 9/11, and one can speculate about what was going on around that time period. It's also really interesting to see in 2015 data, kind of this huge word, and in 2016 data has kind of shrunk down, which is interesting for us.
So just what is data science and how did we make these visualizations? Well, we started our class by looking at this data science Venn diagram, which encompasses hacking skills, math and statistics knowledge, and substantive expertise. So the hacking skills is where computer science comes into play. It involves like manipulating text files, understanding vectorized operations, thinking algorithmically, and a lot more. So for the math and statistics knowledge, it's not really anything too special a lot of the time. Like, you don't need a PhD in math, but you definitely need to be able to appropriately use math and statistics to extract insight from the data. So for substantive expertise, it's a lot of the time like being an expert in your field, like biology or economics, and being able to apply it to your results. So without getting into too much detail, this is like a little bit about the data science process itself and how you can obtain that Venn diagram. So a lot of the time you start with a hypothesis and you want to explore a question. So for us, we wanted to address questions regarding the history of the Ruhlman Conference over 20 years. So the next step is sort of like to find the data, whether it's given to you or if you have to collect it yourself. So for us, we were given all the data over the last 20 years. So once the data is obtained, it needs to be cleaned and explored before it can really be used and create visualizations off of that. So with clean data, you can then make models. And from the models or visualizations, people who don't have the substantive expertise in the field, they can often understand the data in ways that they wouldn't otherwise. So for all of you, we went through this process so you could get the most out of all the past Ruhlman data.
Okay, so where does this data actually come from? So the very start of our process came from PDF files from all of the Ruhlman books that are printed out. But the problem with this data is that it's in PDF form, so it's basically images. And they're completely inconsistent formats throughout the year, and it's also very messy data.
So this is what we had to work with in order to get our data that we wanted. We started with scanned images of programs from 1997 until 2016, and we wanted to get from that into a nice organized format like you see on the right, with information like the year of the program, the title, the abstracts, and the advisors and students that participated in that year. First, we had to take those scanned PDFs and then turn them into text files. This is our first attempt. As you can see, this would be impossible to work with. And after much trial and error, we turned to LTS, and we'd like to thank them for successfully converting our data, because without them, none of our analysis would be possible, because we'd have completely bogus data.
So this is what we received from LTS. Thank you again. Every year was formatted really differently, and we had to spend a lot of time reconciling those differences because the data was captured differently over the years, and the data was formatted differently, and the exceptions and mistakes in each year were also different and had to be accounted for in every different parser. And just as importantly, each of us was defining clean in a different way. So a lot of this was not just about cleaning the data, but about communicating with each other.
So here we have the formatting of the abstract section that we looked at in the Ruhlman programs over the years. So as you can see, in 1997, the majors of the students weren't given to us. So for that section in our student majors, we just left it unspecified because we could not get that information. And then from 1998 onwards, we had got the majors. However, the format was student, major year. And then in 2001, that changed to student year, major. So people dealing with these documents had to parse this particular line differently. And then in 2005, we got more information in our title sections. So for talks like small panels or small talks, we got information on the style of the presentation as well as the location of the presentation. And so we had to figure out how we wanted to deal with that data as well. And as you can see, there were slight variations in the presentation of the data over the years. And since we were working in a big group, individuals had to figure out how they wanted to parse their own documents. So creating a standard formatting for each of these sections was very difficult, and that was one of our biggest challenges.
So finally, after a lot of scrambling and fixing small bugs and compiling issues, we finally got a manageably clean sheet. Definitely not perfect, but it's about 3,000 lines long, 20 years of data. And each line is a distinct presentation. And in this format, we were able to do a lot of project-based analysis, like word-based analysis, such as the word clouds that you saw before. And we can study topic trends over time, answering the question, what is Wellesley interested in talking about? How have those interests changed over time? And also studying the interdisciplinary connections evidenced by student collaboration in Ruhlman projects.
While organizing our data, we used a data organization theory called tidy data to perform our analysis. Tidy data uses a theory of observations as rows and variables as columns. So an observation can be defined by anything, but it was presentation in one of our analyses, but it could also be a student. Or as you can see here, it's either a patient on the left or a treatment on the right. And different observations are better for different analyses. So, for example, like Amar said, the presentation observation worked well for presentation-focused work, but if we wanted to study individual students and how students participate in the Ruhlman Conference, then we had to make a tidy data data frame where each student was an observation, as you can see here.
Yeah, so I was tasked with this. project, and through this task I learned a lot of things, most of which has to do with the truth and the magic of the 80-20 rule. When I started to look at the data from a wider lens, I noticed that every year was formatted really differently, and we had a lot of inconsistencies still, even after all this cleaning. And I was getting really frustrated, and Annie told me, don't try to make the data perfect, just try to get at least 80% of this data and turn it into a student, like a student-centric data frame. And lo and behold, I translated 83% of the data from our original presentation. And to drive the lesson home further, I definitely felt like I spent 20% of my time working on that first 80%, and the last 20% of my time picking out the little things in my parser to maximize output.
This is an example, going back to parsing throughout the Word documents, of how we converted Word documents to data frames that we can use for analyses. So this is a sample Word document that is very clean, and all of them do not look like this, which is part of the problem. And then the code on the right would take this and then turn it into a data frame that we could then use to run our analyses. It would break off those squared off pieces, and it could recognize which was the title, which were the students, advisors, and abstracts, and then break them down into a usable format. We then took the results from that code and then parsed through it again in a second round of parsing to take out items like the student year, the advisor's department, and the student major or majors if there are multiple students in the same project. All of this, as the students have said before, had to be formatted differently for every single year, so it took an enormous amount of work. So this cleaning and going through the data and making sure it was all usable took an incredibly large amount of time, and the vast majority of our time while working on this project, but we considered it a time investment because this data didn't exist in a usable format before, but now people can take it and use it for their own projects, so it's more, once this data is created, it can be used an infinite amount of times, and people can explore different paths using our data that we made.
So now that the data has been cleaned, we decided to explore it, and then we can model and create visualizations out of the results. So in this portion of the presentation, we will show you the visualizations that we created. We'll show you the ones that worked, the ones that might not have worked as well, and so hopefully you guys will appreciate that.
Great, so I calculated how many Ruhlman presentations each department had advised over the years. To get a better idea of this, we can look at the interactive version of the graph, Hannah. Thank you. So you can see that the top two departments are biological sciences and chemistry. If you hover over those first two on the left, you can see they're separated by only 3 presentations over a total of 20 years. So upon digging a little deeper, it became clear that these departments dominate because research is really such a big part of majoring in biology or chemistry. Chemistry majors actually have to have some sort of independent research and a presentation, so it makes sense they would end up presenting at Ruhlman. This analysis presented some really unique challenges. As we were talking about that 80-20 rule, I definitely spent 80% of my time doing 20% of the actual cleaning of this data. One of the main reasons for this is because departments changed names over time and changed formats. So cinema and media studies was once film studies before CAMS existed. Women's studies became women's and gender studies. Then there were some kind of odd typo type ideas here. There was one full year where women's and gender studies was woman and gender studies. There was another year where it was just women without the apostrophe S. A couple thrown in there just said women's without anything else. So when you're dealing with, I believe it was 3,015 separate abstracts that we were pulling through, trying to find all those little differences was a challenge. There's also the fact that art, studio art, and art history are different. So trying to figure out when specific changes within those occurred over the years was another big challenge. And this I find pretty interesting because if you scroll towards the end, you could see which majors kind of have one presentation. So you find some really interesting individual majors. There's urban studies, quantitative reasoning has one, media arts and sciences has one presentation. That's not because MAS majors had one. Remember, this is the department. So it's because the MAS professors are usually CS professors and the combination of the arts and other things. So it kind of is an interesting breakdown of departments at Wellesley and who does what.
Similarly, I made a graph that basically does the same thing, but instead of focusing on the faculty departments, I broke down the major of the presenters. So you can see psychology is has the most people who have presented the psychology major. And at the end, again, ran into the same problems where I had like 30 just women major. And this majors presented a particular problem because I had to work with not only MR's 83% of the data, and then some of that I also ran into problems as Nina Marie had, such as women or parsing errors or change in department names. It's also interesting to note that although biological sciences was the first one for the departments, as seen in Nina Marie's graph, psychology is the first one. And actually, this is a little bit chopped down. The first one is psychology, and then English, and then econ. Biological sciences is the fourth most common major. It's condensed a little bit so you can see the entire graph. But it's interesting. It's probably potentially due to the fact that one faculty advisor may advise multiple students, such as for this panel. So for example, this panel, we have one advisor in the computer science department, but not all of us are computer science majors. There's 11 of us from various disciplines and departments.
So to bring it back to department data for a moment, this chart and analysis was done by Megan O'Keefe. She's a senior who unfortunately couldn't be here today, so I'll talk a little bit about what she did. So this shows the top 5 overall represented departments by faculty major. It's the top 5 from the portion of my graph I was showing you before. Those 5 are biology, chemistry, psychology, art, and English. So if you look at the trend, you can see that spike in that green line. That's biology in 2005. There was a poster section. There were actually 3 different poster sessions throughout the day. So this kind of shows you how the conference has evolved. Usually spikes do indicate poster sessions for the sciences. At the same time, if you look at 2008 to 2011, the recession years, the 3 sciences have a pretty decent sized uptick. However, English also has a slight spike. So we can't really prove causation here, but there's definitely a correlation, and that's worth thinking about. So does this really have to do with the practicality of projects and people's mindsets during that time? We're not sure, but it's a thought.
So this is a bar graph of student participation as a function of class year, and I think that this graph is pretty intuitive. It makes sense that the beginning would, like the rise in popularity would take a few years for Ruhlman to catch on, and in 2017, 2018, 2019 students, they're definitely underrepresented in this graph, and that makes a lot of sense because they've been here only a portion of the time. I didn't actually look into this, but I do want to figure out why there was such a spike at the turn of the century and why in 2004 the Ruhlman became very unpopular. Oh, this is also me. So this is a student participation as a function of class color. And red class has a mighty win of 6 points above the green class. Go seniors. And purple and yellow are lagging behind with like 50 less presentations. And my hypothesis is that the red class and green class are upperclassmen right now, and so that they've had like an isolated bump in this particular graph. I wonder in 2 years whether purple and yellow would be winning.
So Anne and I then went on to try to understand like if class grade participation mattered throughout the conference. So we thought that seniors would probably be overrepresented, which you can sort of see through this stacked bar chart. So we determined the standing of each student, which is basically whether they're a senior, junior, sophomore, or first year. And then we compared the graduation year of each student presenter to the year of the conference itself. So then we obtained the proportion for each standing by dividing the total number of students in that class by the total number of students presenting that year. So basically we used that data to create this bar chart, but it's pretty visually difficult to understand and interpret. So you can sort of tell that seniors are proportionally better, but then we decided to depict this in another way.
So you can see in this plot, we are showing the same exact data, which grade dominates the Ruhlman Conference. But it's way easier to tell in this graph that the seniors dominate because it's not so full of color and the line is clearly a big gap above all the other years. You can see that the seniors even seem to be going on an upward trend as time has gone on. We also made a plot of just total number of students over the course of the 20 years according to grades. So how many seniors presented, how many juniors presented, how many sophomores, and how many first years presented. Again, you can see that the seniors were really the dominant group presenting enrollment, which might make sense because a lot of seniors are thesising during their senior year and might have to do a presentation for that reason.
As well, so students are very competitive. We wanted to see if anyone's winning the Ruhlman conferences. So our first task was to define what winning would be, and we decided that it was the advisor with the most talks or most hosted presentations that was going to win. So I did this by counting the occurrence of every name. Unfortunately, I ran into the same situation as Nina did, where the input format of the data was very varied. For example, Professor Metaxas occurred in 3 different ways with his first names and initials. And as it was a very easy questions and a very striking sort of headline to it, I wanted to represent it in a very simple way. So I chose a horizontal bar graph as to not distract people into thinking that it's over time. And we can see that Professor Aline is on top with 60 different students advised, or 60 talks advised. And we can see that it goes down very quickly, and already on position 8, they haven't advised even half as many talks. Fortunately, since data is error prone, we've talked about the 80-20 rule already, I was able to manually go and double check everything. And it turns out that even though it's a very straightforward question, there was actually an error margin of up to 10% on each of the things that I wasn't able to work with in any other way. So that just tells us something about how hard it is to actually parse data and how hard it is to actually have everything be clean. What we can learn from this graph is that the science professors are on top. Out of the top 5, there's only one social science professor, and he has been advising, Professor Cushman has been advising the Freedom Project, so that's where he gets a lot of his advisees from. We can probably assume that this is because of the poster sessions and because sciences are more represented in general. And it's also interesting to think about that there are so few professors who have done so many talks. And a question could be, how can we have a wider range of professors be more involved in more talks? Is that something that is beneficial to us? Or is it good that we have a few very well-invested members of the faculty helping us out with Ruhlman?
Okay, so similarly, we saw which advisor won. So which student has won Ruhlman over the past 20 years? And the student is Eliza Heaton, who has presented 5 times at Ruhlman, so go her. There's then quite a few students who have presented 4 times, and then a few that present 3, and as you can see in the graph next to it, it drops significantly, and most of the students have presented only once, most of the students have presented only once. It's also important to note that, just like everyone else, I ran into a lot of problems with names, because the thing is that names aren't really unique. And so for instance, Tiffany Chen, I've been informed that there are 2 Tiffany Chens that are at Wellesley College right now. So sometimes names get repeated, so it's kind of hard to determine, and I should probably go back in and kind of like see when they graduated, and hopefully there's not going to be the same person with, 2 different people with the same name who are graduating the same year, because, but yeah.
How do you do half a presentation?
So it's just the graph that's fallen from, yeah.
So Christina and I looked at interdisciplinary advising. We wanted to know if there were any trends in students being advised by a professor outside of their major, and what we found was that less than half of talks were given by students who were advised by a professor outside of their major. In fact, overall 31% of talks are advised interdisciplinarily. It also seems like there's somewhat of a downward trend in interdisciplinary mentorship, though with the variance in this graph, it's difficult to tell. When we were doing this analysis, we also ran into some issues. As Whitney mentioned before, some student major data is missing, in particular from 1997, and then all data for first years is missing because they're undeclared, and there's no major listed for them in the program.
So this next graph shows presenter disciplines by major. So I broadly categorized majors into social sciences, humanities, and natural sciences. Again, this is a very broad generalization. So first of all, there's a tendency of like subjectivity of the data. So for example, I blocked psychology into social sciences, but there can be an argument that can possibly go into the natural sciences, which would affect the trends that we see here. But as you can see, like it's a little hard to tell because it kind of looks like the natural sciences and the humanities are sort of at the top, and then there's social sciences in the middle. But what's important to note here is that interdisciplinary, and by that I mean that if somebody double majored, that they're majoring in two majors that were not related to each other, so like say like biology and English. So that's what the interdisciplinary line stands for, and other again accounts for all the undeclared or any other parsing errors that we may have run into. And so this next one shows this trend a little bit more clearly. So what I did here is I only looked at the data that was strictly humanities, social sciences, and natural sciences. The earlier data is the lighter colored dots, so like 1998, 1999, and more recent years is 2015, 2016 are the red ones. And as you can see, like towards, like it's all clustered in this one little area, but as time goes on, like it seems to be a trend moving slightly away from majors with social science or humanities majors, moving more towards natural sciences. And while this may not say anything in particular about like the breakdown of Wellesley in general, it does seem to conclude that the Ruhlman presentations have more of a leaning towards natural sciences as time has gone on.
Okay, so in addition to looking at these static graphs, which are really interesting to look at, sometimes it's really beneficial to kind of explore the data. So, so we have this cluster here with words from the abstract and words that appear together. So it would be really interesting to see so the word study and see the connections that the word study has, and how all of these different words kind of group together, and you can select your group and kind of see what's going on. So sometimes it's really good to be able to explore the data more rather than in a dynamic setting, rather than just looking at it statically.
So as Christina just talked about, using exploratory tools is a really, really good way to make data more accessible to everybody, not just data scientists. And data-driven applications is one way that we can do this. So data-driven applications are things like web applications that you can publish online and allow people to explore the data in that way. We've used our data to answer these questions for ourselves, and now we can provide them as a service to other people so they can use that as well. So everything that we've done for this project was in Python, a programming language, and we use several libraries in Python, like pandas, which is a framework that lets us do all of our data analysis, and then as well as Seaborn and Plotly, which are libraries that let us visualize the data like we've shown you before. And then Flask is a micro framework for Python that lets us do this web development and use HTML, CSS, JavaScript to create actual applications online. So I can show you one that we created. This is just a screenshot of it. So for this particular application, you choose a department, and then from there you get a list of advisors from that department who are currently teaching at Wellesley, who have advised at Ruhlman in the past. You can choose an advisor from that list, and then you get this bar graph right here that shows you over the years how many presentations that they've advised on. You also get a number of exactly how many presentations there are overall and how many students overall that this person has advised with. So Professor Cushman was, as you remember from Maya's graph, one of the top professors at Ruhlman. And he's from the sociology department, and this is in case a student maybe was doing a Ruhlman presentation in a major different from their own. As you've seen, Ruhlman is very interdisciplinary, So if somebody, say, a CS major wanted to do something in sociology, they didn't really know the department very well, they could go on this application, look at the sociology department professors and see maybe who they could ask to help advise them. So that could be one potential application for this application. Another one that we have here looks at majors instead. We looked at this data in a different way before. Of how many students in each major presented across the years at Ruhlman. This is a look at computer science. So again, you choose from a list of different majors which major you would like to look at in more detail, and then you can see as a student maybe how many other students like you have presented at Ruhlman in the past.
So moving forward, we're going to be focusing on the abstracts and titles for the rest of the semester. And to do so, we can't really graph an abstract in the same way that we can some of the numbers and advisor counts as my classmates have been sharing. So we need to do a little more processing and manipulating of the data first. And to do so, we're using a technique called clustering, where we group abstracts or titles based on on their content. So there's sort of two different approaches that we're taking. One is the bag of words approach, where we take all of the words from an abstract, we toss it into a bag, metaphorically, we shake it up, and then we count all of the words. We count the number of times that each word appears in an abstract, and then we compare these counts abstract to abstract, and mathematically use the k-means clustering algorithm to clump these sort of vectors of word counts. Another way to do it is using a co-occurrence analysis, which Christina showed you a cluster visualization before, where we looked at what words appeared close to each other in Ruhlman abstracts. So you can do that for each abstract, and instead of ending up with a vector, you end up with a matrix, and you compare these matrices, again using a clustering algorithm to determine which words are closest, or which abstracts are closest together. If you go to the next slide, you'll see some of our preliminary results. These were computed by Megan O'Keefe, and she found, using the co-occurrence clustering, that she could group abstracts into really similar, into categories of really similar talks. So we see here that all of these talks are about children and sort of understanding children's development. And it just so happens that they were able to be clustered because of the word list on the right. So we see this as being a really useful tool for the Ruhlman committee. They can use this tool to cluster the proposed talks, and that way they probably won't have to spend as much time sorting through all of the abstracts when they're trying to put together the Ruhlman program.
So there were a lot of other information in the abstracts. We were only looking at a small portion of the abstracts. So there are things that we definitely didn't account for. And when you're coding, you tell the computer exactly what you want. And so some of the things that we might have missed were images that were included in the Ruhlman program. Committee decided clusters. Now these were like interesting clusters of presentations, which had a unique format that wasn't standard or universal across the Ruhlman program. So we tried to parse those as best we can, but of course we definitely missed some information there. We also didn't account for meal times, which might be interesting to see how the meal times have changed over 20 years. Musical performances are also included. We tried to parse those as well, but musical performances sometimes included faculty members, and since we were mainly focused on students, it's like, how do we account for faculty members? And then different types of presentations. It would be interesting to go back and look at how poster presentations or just talks might have changed, or like how represented that they were over the past 20 years. And unfortunately, Davis scholars and postdocs were left out of our data. Maybe it would be good to go back and like parse that information, but for our purposes, that's just what happened. So
through this project, we learned a lot about what it takes to clean and work with a data set. in data science, there's never a time when someone hands you a perfectly clean and great spreadsheet and says, hey, analyze this. It's always a question that someone has and they want to answer. It needs to use whatever you can get. So we had to go through the process of turning images into data frames that we could use for our analysis, and accurate data frames at that. We also learned a good amount about the 80-20 rule, because a lot of our time was spent cleaning and going through all this data and being very frustrated because we had already had 80% of it done and we were still trying to just do that 20% left. But as you can see, it was very worth it. Also, when looking at this data, we found that we had an overwhelming amount of data and an overwhelming amount of possibilities of things we could explore using this data. So we had to really narrow in and say, okay, we want to see trends over time. Most of our analysis had to do with trends over time, or like who are the most, which advisors have advised the most projects and stuff like that. So we really had to focus in on a certain amount of problems, because if we just tried to cover everything, we wouldn't have any actual results. We just tried to cover too many things. We also learned a good amount about how no department has really dominated Ruhlman. Chemistry and biology are very overrepresented because they just have a lot of presentations. A lot of students participate in panel poster sessions, so there's just a lot of people participating in them. But that points to the benefit of a liberal arts college such as Wellesley, because not one major is overrepresented. Someone can come to the conference and get really just a feel for all the different departments and just see how students from every department work and what kind of research they're doing in their respective fields. We also learned that although no one department does dominate it, seniors are very represented in Ruhlman, but we can also go back and say, well, a lot of seniors do theses during their senior year, so they probably have more to say and just have done more research than other class years. We also came to the conclusion that red class is definitely the best. Unfortunately.
So we would like to thank the Wellesley College Computer Science Department, in particular our advisor and Professor Annie, who helped us so much that this entire project would have been possible without her. As well as LTS, again, for converting our files. It really wouldn't have been possible without them. And we'd like to thank the other students in our CS 249 class, some of them who couldn't present today, but definitely helped so much with this project. It wouldn't have been possible without them either. And we also have a list here of different Python libraries that we used. Thank you. Any questions?
Since you guys talked so much about the difficulties that you face when, cleaning the data, is there any, for future data, are there any like structural ways of entering the data in terms of, for the purpose of collecting data in future?
So each of us made a parser that was specific to the year that we were looking at and we had to clean. So every student in the class was kind of assigned to a year. And all of those parsers are different, but if the Ruhlman program became more consistent in itself, then the parser from the most recent years should work. Also, I think the most recent years were actually we were given an already created data table from that year that we could work with, even though it wasn't in the format that we're eventually using, but there was a data frame for that.
The suggestion that I would have if you're putting on a conference or something like this and really want to know how to format your data, just be consistent. If something you've done for years, don't change it unless you have a good reason. Or if you're going to change it, create another line or something like that, because you'll be saving future data sciences a lot of heartache.
Yeah.
So I'm confused why you always had to work from the PDFs, because I can imagine, at least for the more recent things, that the people who are putting these booklets together have the actual source files that made the PDF. So could you not get any of the source files?
You would think.
We didn't get those.
LTS really did their best.
The last 4 years were spreadsheets.
Yeah.
But all the previous ones, unfortunately, due to the many changes that happen in LTS in terms of systems and how people submit their abstracts, there have been many changes there, so there was no consistency in how. So the most reliable piece of information was the Ruhlman program.
LTS really understood that was difficult. They were handing us a bunch of PDFs and really helped us out the best they could.
I want to compliment you on a really well orchestrated and smooth, collaborative presentation. And I'm wondering if you could tell us a little bit more about the project management side of your work. The fact that you've done all of this in the past 2 weeks is really
If you know this, we all looked at one person at the end, Hannah.
This is our team captain over here. But last Sunday we had a hackathon, a mini hackathon. Yeah, this is a picture of us at the hackathon. And we really put together a lot of the content and did a lot of the data cleaning at that point because we spent a long time together just working purely on that.
Do you want to talk a little bit more about it?
Yeah, it was an extremely collaborative effort. It was very difficult, especially because even just getting the data, collaborating with everybody's schedules and everybody's time, it's hard to be like, okay, you can clean this data set, get it to me by Friday. Like, that's not going to happen as a Wellesley student. So we had to really just work around that and be like, okay, these are a lot of difficulties going on in here. We could see, like, Whitney, thank you so much, Whitney, went through and cleaned our data so much during this hackathon that we did while we were all doing really cool graphs. She was doing the real grunt work of cleaning the data. So in that sense, it was an extremely collaborative effort. While everybody's might not have a really, like, fancy graph to show, everybody's work contributed to the results that you saw here.
I can also say that at the beginning of this, we didn't necessarily establish kind of a good way of organizing our data in terms of the data frames that we turned out. So all of us had different definitions of what was clean data. So we came up with these like CSV files or Excel sheets that we could have considered clean, but they were all different from each other at the same time. So then after we did that, after we did actually a lot of work, we had to kind of change our parsers to make them all the same. Yeah.
We were also fueled by Indian food, Thai food,
I do want to point out one thing for people who might not be computer sciencey people. When we're talking about parsers, what that kinds of means is going through the text of these abstracts and things and separating them, kind of picking a character that would mean that we'll separate it by line, right? So when we had different columns of a student's class year and their name, our delimiter, the thing that we'd separate it by very often was the little apostrophe, thank you, before the zero. And we had another delimiter being a comma for like when I was going through departments, right? So if a presentation was advised by two different departments, my delimiter was the comma, so it would be, okay, count this as a separate thing when you reach the comma. So that's why all the parsers had to be so different, because the formatting of that data with spaces and commas and the order of all of that really was the main issue. So I just wanted to explain what parsing kind of means.
So you've done all this great work collecting this stuff, and you've even, it sounds, designed some web applications that make it possible to interact with. How can you make sure that all the work that you've done is not lost and that people in the future will be able to continue to use that work and build on it?
Well, we'll definitely make ourselves clear. Well, anybody studying the Ruhlman Conference will be able to see our abstract and say, hey, they probably came up with some cool data because we studied the Ruhlman Conference. But yeah, no, that's a really fantastic point because, you know, it's not, someone in the past may have done this and a lot of communications is necessary. Like we said, like the last 4 years actually had spreadsheets accompanying them. However, we had to really go through and redo a lot of that spreadsheet data because it wasn't in the format that was conducive to our research. So it was made for more of like, they had a lot of like email addresses and things that were probably more of like contact information for the Ruhlman organizers. So just communication, even with the organization, of just being like, you know, while you're entering that data, maybe enter it in this format as well. And then just say in a way that's conducive to research so that someone won't have to go through this again and take this really organic approach to parsing out all this data.
Yeah. I mean, it would be really nice if you took the things that you have made and the Ruhlman committee somehow put it as part of, say, next year's website. Yeah. So that when people are exploring the website, they can explore the data that came up to this point, and then maybe someone could be hired to keep the data up to.
Yeah, I mean, even with the cleaning that we did, there were a lot of manual things we had to do. A lot of it was just going through line by line and making sure the formatting was correct in the Excel sheet after we had made a parser that really took out again, 80% of the problems. But yeah, so I think that that's going to be something that has to be done every year, probably even with improvements. But I think that with consistency in the programs, that our parsers from this year should help with it.
And it really would be great to see it on the Ruhlman website, because like we kept talking through this whole thing about all the applications of this data, but that's useless if people don't see it. So, thank you.
Do you think that we could get to a point in the future when we don't even need a Ruhlman committee and the computer can just like...
Yes.
I don't know what the Ruhlman committee does.
Make sure that this day will be a fantastic day that involves a lot of people. So the thinking doesn't involve only the programming, but also how do we make it a great event. But we would definitely share your data and put it online. And if you'll come today to the reception that you're all invited to, A, there will be fantastic food, and B, there is a large tabletop in which all your visualizations are already included. So people have been visiting and seeing them and enjoying them even before the presentation, and you can come and see them included in the tabletop.
So obviously, like some aspects of the Ruhlman committee's planning could be helped out by the stuff that we're doing, but obviously others couldn't because. Yeah, no, I definitely think that's really.
But the clustering aspects, as we were talking about, grouping talks by content. It would be a good place, I can imagine, for the committee to start in the future to kind of see, okay, well, this is what this program shot out for groups. Does this look right to us? What do we think? Instead of having to go through manually from the start.
So do you know what percentage of the students participate in Ruhlman? I mean, is there some benefit of your data? I mean, is there a concern or would there be an interest to get more students to participate? And is there a way that what you've done could get the word out?
I mean, we could definitely do that. I don't think we actually calculated it for this presentation.
Someone did.
Someone did.
But it might not have been one of
We calculated a lot of things over the past couple weeks.
We know it's like 250 students
a year.
Present.
Yeah.
Yeah, every year. Yeah, that's about 10%.
But then you look at what percentage of that is seniors, right? So that's I could see room for improvement there for getting students who are doing these cool things, who aren't seniors, to kind of realize that this is a conference for all of us. Did I see a hand over there, or am I imagining that? No? Cool.
Thank you very much for coming.
Yes.